Okay. I had a very appropriate request to put a little perspective as to what I did last time. I'm not going to really continue what I did last time. I was trying to give techniques, but I want to show sort of the kind of things we're going for. So we're trying to study chordal SLE kappa. And what we're trying to do is study what the curve looks like. And normally what you would like to say, when you're trying to understand the behavior of the curve, you would talk about the derivative or something. But for a fractal curve, of course, you can't do that. So what we'd like to do is sort of describe what the curve looks like around here, let's say at the tip, which is showing, describing how we're progressing. So there's the curve. So if I do that, the natural thing is to map back to GT. And then this neighborhood becomes something like this. And this direction, of course, is the inverse map. And one way of describing the behavior here is in terms of the nature of the derivative from there to there, or from there to there. You can go either way. And in many ways, what we're trying to do is study that derivative for that purpose. Now, if I'm trying to study a curve locally here, or let's put another point z. I'll put it here, but think of this point being close to z. And we're trying to see how this curve interacts near z. There's sort of two perspectives of how to do that. We can grow the curve towards z, or we can sort of like try to start at the tip and grow backwards in a reverse direction. What I was doing yesterday was the starting near z and going backwards reverse perspective of what the curve looks like, roughly speaking. Today, which will be separate from what I did yesterday, we'll be taking the forward perspective of looking at the curve as it gets close to z. Now, some of the things I talk about today may have been done in the foundational course, but if there's some overlap, that's okay. But here's the question. So we take SLE kappa. And we take z in the upper half plane. And we ask the basic questions, well, is z on the curve? I assume this was mentioned in the foundational course, but the answer here will be yes, if and only if kappa is bigger than or equal to 8 with probability 1. And we will, as we go along today, we will also see this along the way. So we will see the plane filling nature of it. If not, how close does it get? So that's a probability that the distance, let me just write gamma. I'll just write gamma for the entire curve. Can I give the asymptotics for the probability the distance gamma to z is less than or equal to epsilon? And this is related to what's the dimension of the curve? Say Hausdorff dimension. And let me just give the heuristics in case you haven't seen this, how you do the envelope calculations for random fractals. So let me just I'll often restrict to a domain D up here that's bounded, both bounded and bounded away from the real axis. And suppose I have a curve going through here think of a fractal curve, and I'm interested in the dimension of it. So let's just focus on gamma intersect d. So we're in a bounded set. And let's cover this set by disks of radius epsilon. Then the number needed should look like epsilon to the minus d, where d is the fractal dimension. Now, I'm using the word fractal dimension because there are a couple of different definitions of fractal dimension. Box dimension, Hausdorff dimension, all of which are like this. This is actually closer to the box dimension definition. But for the sets I'm talking about, they'll all give the same number anyway. But this is. Now, if I take a z in D, whether or not z is in one of these balls, disks, really has to do with is the distance between z and gamma less than or equal to epsilon. So we can cover, let's cover D by, well, epsilon to the minus 2 about disks of radius epsilon. So that's just covering all of D. And so the expected number needed to cover the curve is epsilon to the minus d, which of course is epsilon to the minus 2 times epsilon to the 2 minus d. So the idea of this is for a given disk, the probability that it's needed is epsilon to the 2 minus d. And so this intuition should show that this distance, as epsilon goes to 0, so as epsilon goes to 0, this looks like, well, there might be some function of z, but then epsilon to the 2 minus d. Okay. Yesterday, I really didn't give too much perspective of where things were coming from. I'd like to show where things are coming from this thing. So what we're going to do now is suppose such a function exists. So let's suppose a g exists and a d. So a g and a d, so that this is true, so that probability that gamma, distance from gamma to z is less than or equal to epsilon, should look like g of z epsilon to the 2 minus d. Actually, I should make this a much stronger thing. And the question is, can we determine what g epsilon has to be? When one does these questions, there's generally a two-step process when you look at things. First is you see something that you think ought to be a martingale. Then if you think it ought to be a martingale, then you say, well, if it's a martingale, then you've got to satisfy some differential equation. Then you find the solution to that differential equation. And then you go back, and once you have that solution, you have your martingale, and you can work from there. I'm saying this because something I didn't do yesterday was tell you where martingales came from. I pulled the martingale out of the hat. So from a mathematical perspective, when you're just giving a proof, it's perfectly acceptable to pull the martingale from the hat and go from there. But there is a way where you've actually derived the martingale along the way. Okay. Now, before you're continuing here, I'd like to set up a little notation. Turns out distance is not the best thing to look at because it's not quite the best thing under conformal invariance. So definition. If D is a simply connected domain, this D is not the same as that D. Sorry. And Z is in D. I'm going to let upsilon D of Z be equal to 1/2 times the conformal radius. But I'm going to now I will define conformal radius. Or actually, I will define 1/2 conformal radius. 1/2 conformal radius is the following. So if f from the upper half plane into D is a conformal transformation, with f of I equaling Z, then this thing is equal to f prime of I. So for instance, in the upper half plane, the conformal radius, this is equal to y. Usually conformal radius is defined by taking disk to D with f of 0 equals z, and then you get a factor of 2 difference. It's not important, but we're working in the upper half plane. We might as well make the upper half plane the nicer thing. Let me also define in radius. Some people sometimes just I'll call it in radius D of Z is just the distance from Z to boundary D. When people talk about radius in conformal world, there's actually 3 things they can mean. They can mean the conformal radius. They sometimes mean the in radius, and sometimes they mean an analog of the diameter but centered at a point. There's 3 different meanings, so I won't use the word radius. I will use in radius and conformal radius. And fact, which is an easy consequence of the Kirby 1/4 theorem, is that 1/2 in rad D of Z is less than or equal to this conformal radius. I'll just say conformal radius. I won't say 1/2 conformal radius. So up to a factor of 2 on either side, these quantities are the same. there's one other quantity I want to discuss, and that's just the sine of the angle. So here, so that this is definition, or it might be a just notation. So suppose D is simply connected and suppose W1 and W2 are distinct points on the boundary and Z is in the inside. Then with respect to W1 and W2, Z has an argument. So let F be a conformal transformation from D into the upper half plane with F of W1 equals 0, F of W2 equal infinity. Then we define S. S stands for sine. And it's the sine of the argument of F of Z. Rather than defining the argument, the sign turns out to be more convenient because I sort of want to treat things near 0 and things near pi being the same or being the same. This conformal transformation is not unique, but it's unique up to a dilation at the end. So the argument is determined. We have that. And then we have the rules under conformal transformation, which follow almost immediately from the definition. If F from D to F of D is a conformal transformation, then the conformal radius gets multiplied by the appropriate radius, appropriate derivative. And the angle is a conformal invariant. And the goal for today is basically to show there exists a function I'm going to call it G star. I'm going to eventually give you a G, but this is up to a multiplicative constant. So G star, which depends on Z, Z W1, W2, such that if gamma is SLE kappa, here kappa is less than 8, from W1 to W2, in D, then as epsilon goes to 0, the probability that, oh, I guess I need one more notation. So let me draw a picture here. There's W2, there's W1, there's Z. So maybe a little notation here. So here, this is the curve up to time t. Let me just call that the curve up to time t. For what I'm saying here, the exact parameterization of the curve doesn't make any difference. You can parameterize it however you want. Then dt is the component of d minus gamma t containing W2 on the boundary. So in the case of the upper half plane, dt is the same thing as ht. Let me write, in this case, upsilon t to be the conformal radius in dt of z. And let me write upsilon infinity be the limit as t goes to infinity. So it's basically the conformal radius of z in this domain here. If by chance, if z gets, well, actually, that's yeah. Then the probability that this is less than or equal to epsilon at z is asymptotic to this number times epsilon to the 2 minus d. And I haven't told you what d is yet, by the way. So there exists a function and a d. And this is as epsilon goes to 0. So now we're going to try to prove this theorem. And to start to trying to prove the theorem is to figure out what the function in D would have to be if this has a chance of being correct. So there's Z. Here's gamma up to some time t. Here, so now we're in the upper half plane, and we can use the capacity parameterization. Now let's not worry about the subtleties, the limits. Let's just assume epsilon is small. So let's assume epsilon is small enough that our curve hasn't hit there yet. And let's consider the probability that this is less than or equal to epsilon given, all right, given gamma t. So for those who want to be precise, what I really need to do is take a stopping time here that doesn't allow me to go into this circle. In fact, I should probably think in terms of stopping times. Well, as epsilon goes to 0, what we know about SLE is that it continues as if it were SLE in the slit domain. So let me just say the asymptotics of this should be G in the new domain. So in this, we call that HT in the upper half plane. HT is the slit domain. Z, now this point is what I call gamma of t. So my notation, I write gamma of t for a particular point, gamma sub t for the entire curve. And then this will be, again, epsilon to the 2 minus d. Well, let's move this picture by G sub t. So there's gt of z. There's ut. Now, if epsilon is small enough, a ball goes to just about a ball. So here, this is epsilon, just about epsilon times the derivative at z. So I can also think of this as being G in the upper half plane from ut, from ut to infinity at gt of z. But I would have gt prime of z to the 2 minus d, epsilon to the 2 minus d. And by translation and variance for SLE, this should be the same thing as gt of z minus ut going from 0 to infinity. And basically, as epsilon gets small, we have this asymptotics. So what we would expect is that, in fact, if I divide by epsilon to the 2 minus d and take a limit, one would expect that this should be a local martingale. So G star HT Z gamma T infinity should be a local martingale. Taking conditional expectations basically gives me martingales, except that I do have to worry about this making a stopping time. So these stopped processes give me martingales, and therefore I get a local martingale. And over here, we get that this is the same thing as gt prime of z to the 2 minus d g of zt of z, where I write, or g star is, okay, star of z for from 0 to infinity. And going back to the paper of Rode and Schramm, they didn't quite use this notation, but it's basically what they did, was basically they said, suppose phi is a function, smoothly C2 function from the upper half plane into the positive numbers. Such that, well, we have to have a scaling relationship. Phi of RZ equals R to the D minus 2 phi of Z. I leave this an exercise that if we have the scaling here, you get when you dilate or expand the half plane, you get a relationship. And gt prime of z to the 2 minus d phi of zt of z is a local martingale. Then phi is equal to some constant times g, where g of x plus I y, well, g of z is equal to the imaginary part of z to the d minus 2 sine of the argument of z to the 4a minus 1, or 4a, this is 8 over kappa minus 1. So here, let me restrict here to kappa less than 8. I promise you I'll actually show you why you can tell kappa less than 8 is where we want to restrict it by. But so this is an Ito's formula calculation. I'm not going to do it. But I just wanted to say that this determines the function uniquely by these properties. It also, it also determines d. And d must be equal to 1 plus kappa over 8. 1. Sorry. It also determines d. And in fact, in their paper, Basic Properties of SLE, they did this, made the conjecture that this gave the Hausdorff dimension of the paths. They proved the upper bound in the direction, and they gave, well, a good argument why we would believe the lower bound to be true, but they were far from the step away from the proofs. So for the rest of today, I may use D, and by definition, D equals 1 plus kappa over 8. Right now, I'm not assuming any theorems about that, except for, well, we get this theorem here, which is, but I like using D because I remember it always reminds you what the dimension is. So, 1 plus 1, this is just written in terms of A rather than kappa. 1 plus 1 over 4A. It just put 2 over, kappa equals 2 over A. Yeah, 1 plus 1 over 4. So definition, the chordal SLE kappa Green's function and this is only defined for kappa less than 8 for SLE from W1 to W2 in D is well, it's the conformal equivalent of that, wherever it is. That imaginary part, the important part about that's actually the conformal radius. So it's the conformal radius of D in Z, or raised to the D minus 2, and the other is the sine term. Today, exact values may not be so important, but it is important to remember throughout. This is a number between 1 and 2 for the kappas we're interested in. And this is a number bigger than 0. This is kappa less than 8, so which is A bigger than a quarter. By the way, something I was going to do, and I want to do it now in exercise, when I do some stuff tomorrow, estimating the sine, I want to give a sort of an exercise. So suppose suppose simply connected D with boundary points W1 and W2, interior point Z. Then let's write boundary D as W1 union W2 union A1 union A2, where I'll just draw the picture. There's W1, there's W2. I don't care which one I call A1 and which one I call A2, but they're the two connected arcs on either side of it. Then there exists an absolute C such that, so it doesn't depend on our choices. such that this is comparable to, so say C1 this is less than or equal to, and I'll have to where HM stands for harmonic measure. So if I take a Z and I do a Brownian motion starting at C, I can ask, what's the probability the Brownian motion ends up at A1? What's the probability the Brownian motion ends up at A2? Take the smaller of those two numbers, and the smaller of those two numbers is comparable to the sign. Step one of this exercise is it's sufficient to prove this for the upper half plane by conformal invariance. Okay. So now that we know what our martingale should be, and I will write just G for GH 0 infinity. So now we have m sub t, which depends on z, which is gt prime of z to the 2 minus d times g of zt of z. And this exercise, or the work of Roeder-Schramm, shows us a martingale, in fact, or a local martingale. This satisfies dmt equals 1 minus 4a xt over xt squared plus yt squared mt dbt. So, and again, and as in the first lecture, bt is minus ut. Again, I'm not going to do the computations today. So now let me be in the upper half plane, look at z, and the question is, what's the probability that I get close to z? And it turns out when I'm actually focusing on curves as they get close to z, it's useful to have a parameterization that focuses on z more than infinity. And for this, we're going to choose radial parameterization. So we will, so unless I say otherwise, we have fixed some z in the upper half plane. And now we're going to do a radial parameterization. in the radial parameterization, basically what we're going to do is we will, well, I'll just define it. I'll let sigma of t be the first time, and I'm going to choose a particular version of this that turns out to work out nicely, but that gamma of s is equal to, I mean, epsilon of s, e to the minus, I'm going to choose 2a times t. Choosing e to the minus 2a times t is an arbitrary decision. You might just choose e to the minus t, but I would have to do a change of variables later on. I'll just do it this way. But the important thing is that the log of epsilon is growing linearly. So log epsilon of sigma t decays linearly. It's getting smaller. And again, I'm not going to do the computations. And this computation essentially goes back to a paper of Schramm. But I'm going to let capital theta of t be the argument of z at time sigma t. Oh, I should also say it's possible for many paths that they won't get that close. I mean, some paths, so there will be paths for which sigma t is infinite. So sigma t equals infinity if at time infinity, if we never get there. And then the fact and why I chose the minus 2a in there. Fact. Okay, this doesn't require any I didn't say anything about the distribution here at all. I mean, that's just a Lerner equation. But for SLE kappa, there is a standard Brownian motion, which I'll call WT, such that d theta t equals 1 minus 2a cotangent theta t plus dwt. So the minus 2a was chosen so that w would have variance 1 at that point. So let's look at this equation. In fact, let's look at I've gotten the habit of calling this a radial Bessel equation because it looks very much like a radial equation at the endpoints. Here, theta t is restricted, well, it's restricted to this, but I stop it if theta t becomes 0 or pi. I'm not going to go beyond that. So by comparison, with the regular Bessel process, theta t reaches 0 pi in finite time. if and only if the corresponding Bessel equation reaches the origin. So that's beta less than a half. So that's just the fact the Bessel equation. Let me just, beta is 1 over 2. This is 1 minus 2a less than a half, which is a bigger than a quarter, which is kappa less than 8. So this statement is valid for all kappas. The reason I just say this, in case you didn't see it before, so what happens here, if kappa is less than 8, this equation dies in finite time. What that means is there's a finite time, well, in the infinite capacity, by the time the half-plane capacity is infinite, that's only a finite amount of time in the conformal radius. That means we haven't reached the thing, reached z. If kappa is bigger than 8, bigger than or equal to 8, this thing lives forever, which means that the conformal radius gets arbitrarily small, and okay, you need an epsilon more argument to say because the conformal radius gets arbitrarily small, you actually get to z. Okay. So I promise. So that's where you see that kappa bigger than or equal to 8 is space filling. We'll reach z. That's all I want. Okay. Now for the rest of this lecture, even if I don't say it, kappa is less than 8. Okay. Maybe I'll stay in capacity parameterization for a second. So here's my martingale, my equation. By the way, so for kappa less than 8, so for kappa less than 8, with probability 1, limit as t goes to infinity, mt of z equals 0. You can see, well, you can see that if it was still up there. Basically, if the curve goes to infinity, the sign goes to 0, and the conformal radius stays away from 0, and you get this. And it's sort of the mt blows up on the event that z is in the curve, which is an event of probability 0, but I get closer and closer to it, actually blows up. And what you can check from this is, in fact, mt is not a martingale. In fact, expectation of mt of z is strictly less than m0 of z for some tp. Actually, it's not for all t's, for some t's. But I can still use Kirsanov. I can still weight by this thing. I can still weight by the local martingale. And this tells me what my drift term is. Okay, maybe I won't write it out because I'll skip now to the, so in the radial parameterization, one thing I forgot to mention, many of you have probably worked it out already. Those of you who know radial SLE, I'm sure everyone here does at this point, there's a certain way that one parameterizes radial SLE. And that is essentially a radial parameterization using 0 as the focus point. So when I talk radial, this parameterization is really the parameterization coming from radial SLE up to a linear time change. In the radial parameter, if I let mt hat, which is m at sigma t, actually is a martingale. The only blow-up occurs when z is actually, when you actually get to z. For every fixed time t, the radial parameterization hasn't let you get close enough to blow it up, for it to blow up. And in this case, the martingale is actually just, well, okay, it's epsilon of sigma t to the d minus 2 sine of argument z sigma t to the 4a minus 1, which is, and that's constant, e to the 2a 2 minus dt times sine theta, sine. Actually, I meant to circle here. And dmt hat turns out to be equal to 4a minus 1 cotangent theta t mt hat d, whatever I called the Brownian motion all the way down there, wt. And so we can weight by the martingale. It's an actual martingale, so there's no problem using Girsanov here now. Let me use P star and expectation star for the new measures, so that dwt equals 4a minus 1 cotangent theta t dt plus d hat t. So in this case, so this is now a Brownian motion with respect to this measure. And then using the equation over there, d theta t equals, well, 4a minus 1 plus 1 minus 2a And now let's look at our beta again. So now, if 2a is bigger than or equal to a 2a is bigger than or equal to a half, which is a bigger than or equal to a quarter, which is kappa bigger than or equal to kappa less than or equal to 8. That implies solutions exist for all time. And what this should be thought of, this process weighting by this martingale should be thought of as SLE kappa conditioned to go through the point Z. And that's a definition. Two-sided radial SLE. And we'll do it in H from 0 to infinity, going through Z. Stopped at TZ is, and I'll just say SLE kappa weighted by MT. I can give the same, it's convenient to tricks to the radial parameterization when discussing this, but I could have also written it in the half plane. In the chordal parameterization, this process will die in finite time, because by the time I reach Z, I will not have used up all my capacity. So the reason that term comes of two-sided radial is we view this from the perspective of Z. Okay, let me do it more generally here. I'm thinking of chordal SLE from W1 to W2 conditioned to go through Z. I can also think of that as being two radial paths going out from Z, one from Z to W1 and one from Z to W2 with an interaction. And that's where the word two-sided radial came from it. But it's also chordal SLE conditioned to go through Z. This is the process. So two-sided, if I want to do chordal SLE to condition to go through Z, which is conditioning on a set of measures, that of probability 0, what I do is I do this process until I get to Z. The remainder of it's just done by usual chordal SLE. Once I've gone through Z, the conditioning isn't doing anything more. So that's the hard part to do. Now, given this, it's actually not difficult to prove the main estimate that I said I wanted to prove. Let's consider sigma t of my infimum of S such that epsilon S equals, okay. Actually, for what I'm going to do now, let me just say, let me just write, well, okay, let me just, okay, so I want to know the probability that epsilon s is less than or equal to, epsilon infinity is less than either minus 2at, i.e. that I get that close to SLE, to Z. So that's the expected value of the indicator which is expected value of m hat t inverse and this is the same thing as, this is weighting by the martingale. When I weight by the martingale, I get a probability. I have to normalize by the probability at time 0. So when m0 comes out, expected value starting at star of star mt hat inverse. In this measure, this is always true. So I don't even need to put this in. In this probability, I always get close to that. That's what this, the fact that this lives forever. Okay, yeah. The fact that this lives forever means in this process, I actually hit Z. So this is M0. So this gives me an e to the 2at to the d minus 2, or I can write it like that. So that's the conformal radius part of that, which is deterministic, and we still get sine theta t, in this case, to the 1 minus 4a. And by the way, m0 of z is, at time 0, it's g of z. Well, finally, I have to compute this. Well, now it's, again, one variable stochastic calculus. We've got this equation right here, which is a form of this equation. And and what you need to do is find out the invariant distribution here. Well, for this guy, this is actually among the exercises, the invariant distribution turns out to be sine x to the 2 beta times a constant. Here I've got 2a for beta. So here I end up, the invariant distribution for this gives me a sine theta to the 4a. So I actually get a sine to the 1 power. I do get a constant coming from this normalization here. But essentially what we end up with is some computable constant, g of z, e to the minus 2at to the 2 minus d, And then the one last little bit is, how quickly do you converge to equilibrium here? And that's actually not very here, I'm pushed away from there. In time 1, no matter where I start here, no matter where I start, in time 1, I'm within a constant of my equilibrium distribution, density. And as I keep going, I get more and more time. So this is, my estimate is like 1 plus big O e to the minus some second eigenvalue that I don't really need to know its exact value. And this can be done uniformly over the starting point, at least if I say restrict myself to time bigger than or equal to 1. So I want to sort of just make a formal statement of this. So theorem for kappa less than 8, there exists a u. You could actually find out what u is, but for my purposes, I don't care what they are, such that, okay, here's the such that. If gamma is an SLE kappa curve from W1 to W2 in D, and if Z is in D, and okay, just to play it safe, I'm going to have an R naught, so maybe I should also say R naught less than 1. So we'll only do this for R less than R. Well, I can choose any R naught that I want, but the constant may depend on it. Then the probability that this final conformal radius, the distance, is less than or equal to R times the original distance. So this is the probability that I drop a factor of R, at least a factor of R in the conformal radius, equals, that's, well, the constant that comes from over there. And now all that we have up here is the radius. Sorry, the sign. Right. The sign comes in here. And then 1 plus, in this case, think of little r as being e to the minus 2at. In particular, and this is actually all that I'm going to need, is that this is comparable to the sign r to the, oh, I lost the r to the 2 minus d. Where the constant here, and this is r less than or equal to half, say, where that constant is independent of d, z, w1, w2, and r. It's independent of everything. Maybe restricting r less than half. So if I want to know, no matter, but the key thing is that this is true for every possible domain that you have. I'm going to do some stuff tomorrow which is more complicated getting toward a second moment estimate. And when you do, what we're going to end up doing is we're going to be looking at an SLE curve, and we're going to have to apply this result to the domains H sub t, the slit domain remaining in the SLE curve. Okay, so that's the first, what I kind of call the one-point estimate, done in a lot of detail. I want to start as to what's the work towards two-point estimates. And I'm not sure whether I'm going to have a chance to talk about it, but Vendlin already gave a nice lecture about it. With two-point estimates, you can get the Hausdorff dimension. So with a good two-point estimate, as of the kind I'm going to mention in a second, one can prove, using what are at least now standard methods, that Hausdorff dimension of gamma equals, oh sorry, that's the wrong, equals D with probability 1 for kappa less than or equal to 8. And here's the main estimate, and first proved by Vassal-Bafara, or essentially proved. I mean, I can say slightly stronger than what he proved, but he could have proved. He could have. Okay. Suppose D contained in H is a domain whose closure is still in H, is a bounded domain. So here's H, here's D. Actually, the one thing we're going to use about D is that the Green's function is uniformly bounded above and below in D. Then there is a C, which can depend on the domain. Such that for every epsilon bigger than 0 and delta bigger than 0, and ZW in D, or the closure, you can put them in the closure if you want, the probability that I get within epsilon of Z in the conformal radius sense, and I get within W, delta of W, is less than or equal to constant epsilon to the 2 minus D, delta to the 2 minus D, Z minus W to the D minus 2. Let me just make a couple of comments about this. Well, okay, let me just, okay. The hard case is not really when Z and W are close to each other. It's when Z and W are far apart. The hard case, if Z minus W is greater than order 1, to show when they're close together, basically, I'll just do a little picture for this. So suppose they're close together. Let me assume epsilon is bigger than delta. And let me assume epsilon is also smaller than Z minus W. If epsilon's bigger than Z minus W, this is easy. You just have a 1-point estimate. The basic idea actually is, well, wait. If Z and W are close, what I do is I draw a disk around Z of radius maybe 10 Z minus W. So there's Z minus W. Now, if I'm going to get close to both Z and W, well, first thing I have to do is I have to get here. So I have to get there. And then that gives me a Z minus W to the 2 minus D. Because that's the word. I'm not going to worry about the constants. Now let me conformally map this. Okay, now, in reality, of course, this is a small number. So this is, but what I'll do is I'll map this back, but blow it up so that Z and W are macroscopic. The important fact that's used, and it's used in some other things, is too. A beautiful thing about conformal maps is not true for general functions. So here we have Z and W are distance this apart, so that their distance is bigger than a constant times this radius. Well, I mean, we already have seen that. Let's just call this time rho. So the distortion theorem tells me that G prime at Z and G prime of W are comparable. You also get that, of course, Z minus W, and if we have uniform bounds on the derivatives, we get that's less than or equal to, sorry, I mean Z, I mean G of Z. Yeah, sorry. So this is actually G rho of Z, G rho of W. So G rho of Z minus G rho of W times Z minus W. Here we're using the fact that the derivative is comparable everywhere there. But the other thing is we actually have an inequality in the opposite direction. It works both ways. And that's basically the Kirby 1/4 theorem in action. If I draw a ball here, a radius there, then this thing includes a certain radius over here, and G rho of W is not in there, so that protects this. So by just these sort of estimates, once I get close, Z and W are far away, so it turns out we end up with 2 extra factors of Z minus W to the D minus 2 on twice. If I do the estimate there, I can do that. If I can handle the case where they're apart, they can do it. And this actually is not an easy thing to do. That's what I'm going to do tomorrow. I'd like to actually give one more exercise. Which actually is important. Because I'm going to convert, actually, tomorrow from working with conformal radius to actual distances. So as before, let rho of t, no, sigma of t, be the first time that the conformal radius is less than or equal to e to the minus 2at. Now, conformal radius is almost the same thing as distance. Let me just define the same thing for distance. I'll call it rho of t, such that distance, or well, I can actually just use distance in this case. I can just use the curve, the first time I actually get within distance. The first thing is that these are virtually the same up to a constant. So but there's a little difference in this. This guy doesn't, sort of is kind of not continuous, in the sense that my curve gets some distance away, then it leaves, and it messes around for a while before it actually gets closer again. This guy actually grows continuously. So this guy is growing. So the conformal radius actually grows here. So the conformal radius can grow without the distance getting closer. However, the important fact is that if the distance gets closer, then the conformal radius does have to grow. So if I so okay, maybe just okay. It would just stay that way. So if if I know the distance has gotten closer to me, like if I've started there and the distance has gotten closer, not only are the parameterizations of order 1 of each other, but in fact, the conformal radius also has to have, logarithm has to have dropped, right? Or the time. So maybe I'll just, part of the exercise is just to state it and finish this up. So if I start here and the curve comes in somewhat, then the conformal radius grows. Okay, so I think I'll stop there today. I haven't successfully managed to post notes, but I do have, you can just download them from me if you want. So anyone who wants them, I can give you the file that you can put into your computer, at least the current updated form of it. That's. Well, I sent it to somebody and never got posted, and they. Is there some? Anyway, what I have now is more updated than the last thing I tried to post there. So if you're interested, you may want to. Yeah. Okay.